Hello and welcome. Today we're going to dive into a family of chemical compounds that are, well, they're everywhere. Seriously, they're in our medicine cabinets, they're in industrial solvents, they're all around us. We're talking about haloalkanes and haloarenes, the powerful, essential, and often kind of invisible players in our modern world.
So to kick things off, I want you to think about this question for a sec. What's the link, the chemical link, between a life-saving treatment for typhoid, the medicine that fights malaria, and the anesthetics that make modern surgery even possible? I mean, on the surface, they seem totally unrelated, right? But believe me, there's a very specific common thread hiding in there.
And the answer is halogen-containing compounds. Yep, chloramphenicol, chloroquine, halothane, every single one of them belongs to this special family of molecules. They are truly the unsung heroes behind some of the greatest achievements in modern medicine. Pretty incredible.
Okay, so now that we've seen just how crucial these things are, let's get down to the basics. What exactly are these compounds that we're talking about?
It's actually beautifully simple. You start with a hydrocarbon, one of those molecules made of just carbon and hydrogen. This could be a straight chain, which gives you an alkane, or a stable ring structure, an arene. Then you just swap one or more of those hydrogen atoms for a halogen. And by halogen, we mean fluorine, chlorine, bromine, or iodine from that special column on the periodic table. That one little swap creates this incredibly versatile class of compounds.
Now, if you want to understand everything that comes next, how they react, why they're so stable, all of it, we've got to zoom in on one specific detail, and that's the bond between the carbon atom and the halogen atom. Chemists call it the Ch-6 bond, and trust me, this is where all the magic, all the chemistry, really happens.
A great way to think of the Ch-6 bond is like an unhappy couple in a chemical marriage. See, the halogen atom is way more electronegative, which just means it has this really strong pull on the electrons they're supposed to be sharing. So it's constantly tugging them closer, which creates a slight negative charge on the halogen and leaves the poor carbon atom slightly positive. This imbalance, this polarity, makes that carbon atom a really attractive target for other molecules, and that sets the stage for basically all the reactions we're about to talk about.
Now check this out, because this is where it gets really interesting. It turns out the identity of the halogen changes everything. As we go down the periodic table, from fluorine to chlorine, bromine, iodine, the atoms get bigger. You can see it right there in the data. The bond length just keeps increasing, from 139 picometers for CF all the way up to 214 for CI. And look what happens to the bond enthalpy. That's just the energy you need to break the bond. It goes down and down and down. The longer the bond, the easier it is to break. And this is just a brilliant way to picture it. Trying to break that short, tight carbon-fluorine bond, it's like trying to snap a tiny, stubby piece of sugarcane. It's incredibly tough. But that long, stretched-out carbon-iodine bond, well, that's like a long piece of sugarcane. It just snaps so much more easily. This fundamental difference in bond strength is absolutely key to understanding why these compounds react the way they do. All right, let's move on to the main event, the chemical reactions. The most important reactions for these guys are substitution reactions, where we just swap the halogen for something new. But it turns out there are two very different ways this can happen. We call them the SN1 and SN2 pathways. So the basic idea is this. You've got your haloalkane with its polar Ch bond, then an incoming group called a nucleophile, which is just a fancy name for a molecule that's attracted to positive charges. It sees that slightly positive carbon atom, and it comes in, kicks out the halogen, and takes its place. A simple replacement. But how it happens, that's the fascinating part.
Okay, first up is the SN1 reaction. You can think of this one as the patient, wait-and-see approach. It doesn't happen all at once in some big rush. Instead, it unfolds in two distinct, separate steps.
So, in the first step, and this is the very slow part, the bond between the carbon and the halogen just breaks, all on its own. The halogen literally just leaves, taking the electrons with it. This leaves behind a flat, positively charged carbon thingy called a carbocation. This first step is the bottleneck, the rate-determining step for the whole process. Only after that carbocation is formed can the second, much faster step happen, where the nucleophile swoops in and attacks that vulnerable positive carbon.
So which molecules prefer this patient, two-step path? Well, it's the ones that can form the most stable carbocation in the middle. A tertiary carbon, that's one connected to three other carbon groups, is fantastic at stabilizing that positive charge. A primary carbon, on the other hand, not so much. So the reactivity for SN1 is tertiary is greater than secondary, which is greater than primary. It's all about keeping that intermediate stable.
Now for the other path,
the SN2 reaction. And this is the complete opposite of SN1. It is not patient. It is a direct, aggressive, one-step process. The key move here is something called a backside attack, and it happens all in one single motion.
In an SN2 reaction, the incoming nucleophile attacks the carbon from the side opposite to where the halogen is. There's no waiting around for the halogen to leave. For one fleeting, high-energy moment, a transition state is formed where the new bond is forming at the exact same time the old one is breaking. The carbon is in this unstable mess, momentarily bonded to 5 things at once, and the whole molecule inverts its shape, kind of like an umbrella flipping inside out in a strong wind.
So what makes a molecule good at SN2? It's all about access. That nucleophile needs a clear path to get in there for its backside attack. A primary haloalkane with lots of open space around the carbon is a perfect target, but a bulky tertiary one, forget it. It's like trying to get through a super crowded room. There's too much steric hindrance, just too much molecular clutter in the way. So the reactivity order is the exact reverse of SN1. Primary is the most reactive, then secondary, then tertiary.
But substitution isn't the only game in town. Sometimes, instead of replacing the halogen, a base will just come along and pluck off a nearby hydrogen atom. This forces the halogen to leave and creates a double bond. We call this an elimination reaction. And to predict what's going to happen, we have a wonderfully memorable rule.
The key to figuring out the outcome of these reactions is something called Ch-6's rule, which is often remembered with this really powerful mnemonic from Hindi, make the pore poorer. Now, what on earth does that mean in chemistry? Well, in this context, a poor carbon atom is one that's already poor in hydrogen atoms. And this simple phrase is the secret to everything.
Okay, so here's the formal rule. When a molecule has a choice of which adjacent carbon to remove a hydrogen from, the reaction will almost always remove it from the carbon that is already bonded to fewer hydrogens. It makes the poor carbon poorer. The reason this happens is that this path leads to a double bond that's more substituted with other carbon groups, and that creates a more stable, lower energy molecule in the end. Nature loves stability.
So we've seen how these molecules are defined, why they're so reactive, and the clever rules that govern them. They are undeniably useful. But that very same chemical stability that we've been talking about, it also comes with a pretty significant downside.
Take chloroform, for example. It was once used all the time as an anesthetic. But if it's stored improperly, exposed to oxygen and light, it can slowly oxidize and form phosgene, which is an extremely poisonous gas. It was actually used as a chemical weapon. This just goes to show that these powerful compounds really have to be handled with care and respect for their hidden risks.
And this brings us to their environmental legacy. That same strong carbon-halogen bond we talked about at the beginning, the one that makes these compounds so stable and useful, also makes them incredibly persistent. As the NCRT textbook points out, they're really resistant to being broken down by natural processes, like by bacteria in the soil. And that means they can build up in the environment and stick around for a very, very long time.
And that leaves us with a final and I think really crucial question. We rely on these compounds for life-saving medicines, for advanced materials, for so much of modern life. But their very nature means they don't just go away when we're done with them. So the great challenge for chemists, and really for all of us, is to figure out how we balance the immense benefits of these molecules with the responsibility of managing their long-lasting environmental footprint.